All right. So the central dogma of ROS navigation is you start with a start location and a goal location. And then you need to get a global plan that goes from point A to point B. But that just tells you where to go and not how to get there. And for that, you need to come up with the actual command velocities that are going to drive your robot along that path. Now, the first step in the process is the global planner, and that's really just glorified Dijkstra's algorithm. And so what we're going to be talking about today is the local planner that covers the second half here. And so just general outline, we're going to start with some fundamentals in theory of how one instance of local planning works, emphasis on the fun. Then we're going to look at how ROS navigation works today, and then we're going to take a look at where I'd like to see it go in the future. So the fundamental question of local navigation is this. What is the best command velocity? And in order to figure out the best velocity, you must answer these questions 3. What command velocities are available? What do the commands do? And how do we define the best command? So let's start with the first question of what command velocities are available. So we're talking today specifically about navigation in 2.5 dimensions, i.e. x, y, and theta. Don't always have to use y, and a lot of the examples won't. So you can define all of the possible search space for local planning in terms of your different velocity dimensions. Here you see that we define a maximum x velocity and a maximum velocity in theta as well. But this just defines the velocities that are available at some point, and not necessarily at the present moment for the robot. In fact, one of the classic methods of local navigation has a problem that is related to this, which is vector fields. So this came out in 1986, and the idea is you have an attractive force that moves your robot towards the goal, and then you have repulsive forces that move the robot away from any obstacles, and then you add them together, you get a combined force, you translate that to a command velocity, and you drive along that. This is one of the classic methods of robot navigation. But if you're very far away from the goal or very close to one of the obstacles, the force vector can be immeasurably high. And so as a result, there are commands that you really can't perform given the acceleration limits. And so that leads us to directly to the DWA algorithm, the dynamic window algorithm. This came out of a paper in 1997. And the idea here is we're not going to look at the entire search space. We're just going to look at a small dynamic window around what the current velocity of the robot is. And the size of this window is dependent on both the acceleration of your robot and some time constant. And that time constant becomes very important in all parts of the local planning. Incidentally, this work was done on the RWI B21 robot, which is the first robot that I ever wrote ROS code for and ultimately released. So when we're actually doing the local planning, we have our search space, we have our current velocity within that search space, and we can define the dynamic window around that velocity, respecting the global maximum velocity. And what's currently done in the ROS navigation stack is a sampling of that space to figure out what command velocities we're going to use. And so we just pick a number of velocities in x and theta and get all combinations. And those are the velocities that we're going to look at. The next question is, what would these commands do? And this is more or less straightforward forward kinematic projection. So we start off with what the current pose of the robot is. We have its current velocity, and then we have the command velocity that we want to send the robot at. And the question is, where would this robot go? We can just project that forward out in time. And there are 2 important questions here in terms of parameters, which is, 1, how far into the future are we going to project this? This is the sim time variable. And then we also have various discretization parameters that define how many poses we're going to put in between the first and last pose. Here's just the one. And so that step is more or less straightforward, but if you have a more complex robot, it can be as complex as you need it to be. And so the real key question is, how do we define what the best command velocity is at any particular time? And so if we have the robot here in the one pose, and then we have 3 options of the last pose of the trajectories for where it could go. And which one we consider best, it's a little subjective, but ultimately we have the general guideline of we want it to move towards the goal and don't hit obstacles. And so in order for the algorithm to actually work, we need to define some numbers for how good each of these is. And we have the guidelines that we say negative scores are invalid. So C hits a wall. We don't want to even consider that one. We give it a score of -1. And then for all the other ones, we say the lower the score, the better. And so A here moves towards the goal, doesn't hit anything. That's going to be our best command velocity at that time. But there are a number of different functions that we have that produce scores. And we're going to call these critics. So critics produce scores for each of the trajectories. And the core of the algorithm is just to take a weighted sum of all the scores. Unless, of course, one of those scores happens to be completely invalid, then we reject the whole thing. And so taking a look at some of the critics that are available, one of the key ones is the obstacle critic, which looks at the cost on the cost map. And so if any of the poses in the trajectory that you generated are in collision according to the cost map, then we reject them out of hand. Otherwise, we just use the cost from the cost map. Then we have the scoring function where we look at the distance to the global path, and that prefers that we stay close to what the global planner gave us. We also have the distance to the goal, and that'll give better scores to trajectories that actually make progress towards the goal. We also want to look at the orientation, especially in robots that are holonomic, like the PR2, that can turn in any direction. And so we look at the orientation to the goal, which will differentiate between this pose here and this one here. Both of them have the same distances, the same cost on the cost map, but one of them is actually facing the goal and therefore, in some metrics, better. Similarly, we would look at the orientation to the global path, which would differentiate this pose and this pose. So these are all the core pieces of what's going on in ROS navigation local planning today. We have, for what command velocities are available, we have the sampling search that we do within the robot's dynamic window. For what the commands would do, we have our forward kinematic model. And then for what the best command is, we have a number of different heuristic trajectory critics that we add together in the end. But what I presented here is one specific way to do local planning. And if you want to do something different, it's a little difficult. So now let's take a look at what ROS navigation is doing today. So theory versus practice. In theory, ROS navigation is a universal black box that runs on hundreds of robots. Now this is mostly true, and what I'm about to say is not in any way to take away from all the work that has been done over the navigation stack in the years, and no disrespect to the people who wrote it. But in practice, ROS navigation was built nearly 9 years ago to control the PR2, and the fact that it works as well as it does on all the other robots is almost incidental. It's a little harsh, but what's important to keep in mind is when it was written, the PR2 looked like this. And so this was a while ago, and the packages that were being used are still being used today. So we have the base local planner that was written in 2009 for Willow Garage's initial navigation milestones. It's so long ago that it doesn't have a turtle name associated with it. And then we have the DWA local planner, which was in 2011/2012, and that came out officially in the ROS navigation stack with Diamondback. And what I talked about in the first part of this talk is exactly what the DWA local planner does. But it's lacking in a couple of particular ways. First, if you look at the inputs that I talked about to the system, we have the robot's current location, its current velocity, the global plan, the goal location, and the local cost map. And if you take a look at the nav core interfaces for the local planner, some of the information is missing. So the current robot location is sort of implicitly in there in the transform listener, but in order to change that, you actually have to broadcast transforms, and that makes testing very difficult. And similarly, the current robot velocity is not in here at all. And so usually it's handled by subscribing to odometry underneath the surface, not through this interface. And so that makes local planners very difficult to test and also very difficult to customize. And so there's one important number here. So looking at the ROS Navigation GitHub page, the most important number is on the top right there, which is there's 519 forks of ROS Navigation. And actually that was true earlier this week when I made this screenshot. It's up to 521 when I checked at lunch, might be even higher now. And what that says to me is that there's a lot of people that ROS Navigation is serving incredibly well. There's lots of people using ROS Nav, that's great. But there's also a lot of, at least 519 people who are saying, ROS Navigation is working for me, but I need it to do something slightly different. And the code that it rests on, there are a number of different problems with it. And what I would like to see in ROS Navigation is code that is these 4 things. Number 1, testable, customizable, backwards compatible, and clean. And so what do I mean by clean? The guiding principle that I use when writing these interfaces is that the structure of the classes in the code should match the structure of the conceptual pieces of the algorithm, which should match the ROS interfaces. In my practice, that's what I found to be the easiest to use. And so that leads us to where ROS Navigation is going in the future. I think there's a lot of interesting work going on, especially what Sebastian and Jorge were talking about earlier. But I've been thinking about the next generation of a lot of different things over this summer. And so what we're announcing right now is the robot navigation stack, a spiritual successor to the previous nav stack that has some additional benefits. And so chief among that is a new definition for local planners. And so here is the updated NavCore 2 interface for local planners. Number of key differences. First, it uses a new package called Nav2D messages, and those use just the 2.5 dimensions that I talked about. And those are used up and down the code to make debugging as easy as possible. Second, we have a more explicit version here of the compute velocity commands function, which takes the pose and velocity in as parameters. And that makes it much easier to test all the different use cases that you might come across while looking at your planner. We have a more explicit version of the isGoalReached function. And then finally, we're doing error handling with exceptions as opposed to just returning a contextless bool succeeded or didn't succeed. Of course, what is an interface without an implementation? So in the old navigation stack, we had the DWA local planner. What we have now is the DWB local planner. It doesn't actually stand for anything, and I'm currently taking suggestions what DWB should actually stand for. And so it has 3 major components. All of these are their own modules. We have the velocity iterator and trajectory generator. We have all the different trajectory critics, and a separate module for the goal checker. And so in that first bit, we have the trajectory generation. So we have a standard iterator interface for iterating through the different velocities, and you feed in the current velocity there. We have the function for generating the trajectory that takes the start pose, start velocity, and command velocity. And then we have all the trajectory critics, people who, or things that will critique the trajectories. We give it the pose, velocity, goal, and global plan initially. Then it can do initial computation so that when we call score trajectory a number of different times with all the different trajectories, we're able to do that in a computationally efficient way. And so this whole reorganization will give a hopefully more logical and easier to test platform. But the key feature here is customizability. And so as the saying goes, when all you have is a hammer, everything looks like a nail. And the hammer that I use liberally is plug-in lib. And so much like we had with cost map layers that allowed you to customize the behavior of the cost map, all of the major modules within DWB Local Planner are plugins. And so you can customize them there. But in addition to the plugin interfaces, we also have ROS interfaces for each of these. So the generate trajectory also exists as a service that you can call, where you give it a start pose, start velocity, and command velocity, and the result is a trajectory series of poses. Similarly, while you're planning, you can also generate this local plan evaluation message. And that has all of the trajectories that were generated, the poses that they go through, and the scores from each of the critics for each of the trajectories. And that way, when you're sitting there afterwards and it's like, why did my robot do this? You can actually go back, check the logs, and see. And I know that, especially within this ROS community in this year of 2017, there's a lot of trepidation about switching from one version to a brand new version 2 of something. I understand that concern, and that's why DWB is also fully backwards compatible. So, and it's that in 2 different ways. One is the interface compatibility. So you can use the DWB local planner in NavCore 1 interfaces just by using a plugin within a plugin. So we have the local planner adapter for that. And then also all the parameters are compatible as well. So if you don't specify what trajectory critics or other plugins you're going to use, it will automatically read your configuration and load the plugins that will replicate what DWA planner would do. And so all this culminates in the ability to control your local planner in new and exciting ways. And so here's 2 examples using the robot that we have at Locus Robotics. So here is an example of precise plan following. And this is just a trajectory critic that I whipped up last week, where it's going to follow the waypoints that are given to it in the global plan exactly. Of course, you can also go the complete opposite way and have something that doesn't follow the global path closely at all. And so here is drunken path planning that just travels along the global path in a sine curve. Please don't drive robots drunk. That's my important announcement. So all this work was done while at Locus Robotics. I had started it during my PhD thesis, but really got the chance to work on it there. So if you're interested in working on cutting-edge nav research, while also having the research deployed with actual customers, our career page is right there. And the GitHub repo's there. Thank you very much.
Thanks, David. Well, while people make their ways to the microphones, I was wondering, you spoke about the NavCore interfaces for local planners, and do you have any comment on global planner interfaces?
Yeah, so I have fewer problems and bones to pick with the global planner, but there are new updated interfaces that have some of the same benefits of how things have changed. And in potential future work that we're looking to put together, we would tackle that as well as different ways to deploy recovery behaviors.
Thank you. I wasn't watching that. Ryan.
Yeah, so I really like the idea of publishing the output from the critics. I was actually debugging a critic like a couple of weeks ago, and I had to go in there and instrument it and have it print out everything I computed internally. That sucked. Have you deployed this yet on your robots, or when, or if not, when do you imagine this new system rolling out into your own production?
So we don't have it in the field just yet, but we do have it on our simulated robots, and so within, I'm not going to project any timelines, but we should have it on our production bots soon. There are a number of different things that we specifically want in our warehouse environments that we can only do with this sort of specialized local planner.
At this microphone, thanks.
Hey there. So one thing you talked about was this forward rollout for the dynamic window approach solutions. And basically you said, yeah, you know, it's really easy to do this forward kinematic thing, and then you can do lots of rollouts. In some cases, I mean, the most trivial case would be that you have some slip in the wheels. But in some cases, this is actually not too easy, and it could be improved a lot by updating your parameters on the fly, or by improving custom forward kinematics plugins. Is that actually possible with the framework at the moment, or did you consider that, or is that out of scope entirely?
So with the DWA local planner, you can only assume perfect forward kinematics, that it's going to do what you tell it to do. I don't have a solution for how to actually handle slippage in the wheels. I know it's something that we as a team are working on. being able to integrate an updated kinematic model into the local planner. So by making that section a plugin, hopefully you could be able to dynamically fix it.
So is there a plugin interface for that at the moment?
For the plugin for the trajectory generator?
For the forward kinematics of the rollouts?
Yeah.
Thanks.
Yep.
Got time for just one more. I'll get the next speaker to come up in the meantime. Thanks.
David, do you have any plans to support different command velocity formats, like maybe Ackermann style?
Yeah, so that is a question that I'd consider. Right now, it does publish Twist 2D messages, not Ackermann. And I debated the best way, if there was a good way to integrate Ackermann, and I didn't figure one.
Okay.
Technically, you could do it, but you would do it by breaking what the Twist message is.
Sorry,
But okay. So short answer is no, it's Twist 2D messages, but you could do it by hacking what the Twist 2D message meant and just changing the kinematics of it. Or we could end up extending it for Ackermann messages.
Okay, thank you.
Yep.
All right then, let's thank David again.